So, we are going to be talking about principles of measurement in this particular section. And the question here is, why can't I report all 10 decimal places from my calculator? Well, as we look through this, you're going to find that it is not feasible to report all the digits that your calculator gives you. You'd spend all your time going through that. And so, as we go into science, we're going to look at what's reasonable, what should we be reporting, how are we going to give these numbers so that we know that we're providing a good response to the question that's being asked. And so we are going to talk about concept of significant figures. Significant figures is any digits in a measurement that may be reported with integrity, including the digits whose values are certain according to the instrument's scale calibrations, along with one estimated digit. And so when you talk about significant figures, you are telling the reader how closely you got to the correct answer. And you can only get as close as your instruments will allow you. And so that's what's important about significant figures is that the integrity of what you are reporting is based on how accurate or precise your measurements are, your measuring devices, as we talked about in the prior section. Accuracy and precision. Well, then now we have to use our significant figures to indicate how closely we are getting to the measured data. Some of the nuances around that integrity. So, data must only be reported to the precision warranted. It doesn't seem reasonable to report 15 digits when I've only measured with an instrument that gives me a certain number of digits. And so, use only the digits whose values are certain, and then you're going to estimate one place of those digits. Zeros might be added when you need to. So sometimes you round and you end up with a zero, but you actually measured to a specific point. So the zero is letting them know, hey, this may be a zero, but I measured all the way to the hundredths place, even though you see a zero there. And so zeros are often added when it's appropriate. For example, when we look at this thermometer, um, we can only be as precise as in between, about halfway in between these is what is typically accepted. And so you could not take this. So if we have 10 places in between our, tens, and that means we have one, two, three, if these are degrees, well, then you're only going to be as accurate to the half degree here because that's what you can do in between here. You're basically estimated in between them. And so the device that we use is going to determine how many decimal places we're going to use. So let's look at these rules. Rule one for significant figures is that they only apply to measured data. So counted or pure numbers are considered exact and significant figures are not applicable. All right. So if you count numbers, then these are you don't have to worry about significant figures. We're talking about measured data, right? So ratios that are exactly one by definition are also exact. So if you have 12 inches in a foot, that is not considered into taking significant figures because you're just doing conversion factors there. And so those equal to one, you've multiplied by one, it doesn't affect your significant figure. Rule number two, all non-zero digits are significant. So if I look at this, 3, 2, 4, and 4, all of those are significant. There are four significant figures here. 62 degrees, 6 and 2, two significant figures. So it's really easy when you have non-zeros. Those don't ever cause a problem. Non-zeros are always significant. So then the next one, if you have zeros that are in between two non-zeros or two significant figures, those are also significant. So my 1, 3, and 3, those are not zeros. But this guy falls in between them. So he's also significant. 1, 2, 3, 4. Again, he falls in between them. 1, 2, 3, 4. There are four significant digits. So if you have non-zeros, those are counted. If you have a zero that falls in between non-zeros, those are counted in your total. Now, this is where it gets a little crazy. If I have a zero after my decimal point, it is significant. The question here is why? Why is that guy significant? Because in the math world, he's not. 30 and 30.0 are exactly the same thing. But in science world, when you're giving data, then what you've told me is, I know you see a zero here, but I actually measured to the 10th place. Or I know you see two zeros here, but I actually measured to the thousandth place. All right. So for this one, my three is significant because it's not a zero. This is significant because it's a zero after a decimal point. And this one is in between two significant figures. So he's also significant. So this is one, two, three. Here, these are significant because they aren't zeros. These are significant because they're after the decimal point. So I have one, two, three, four. This is the guy that everybody wants to mess up. The four is not significant because he is not a zero. This is technically to the right of the decimal, but it's before a significant digit. And so this is my only other significant. That's two. Now I'd like to show you another way to think about it. If I were to write these in scientific notation, everybody remember that. How would I write it? All right, let's look at this first one, 30.0. If I were to write this in scientific notation, remember I have to have a number between 1 and 10. So I would move this over. When you do this, you're supposed to keep all of those. So I would say 3.00 times 10 to the first power. This next one, this is actually in scientific notation already. 6.500. If I were to write scientific notation, I would put times 10 to the 0 because I didn't move him at all. Then let's look at this last one, 0.040. If I were to write this in scientific notation, 1, 2, move it over, I would have 4.0 times 10 to the negative 2. What you'll notice about this is when I write it in scientific notation, 1, 2, 3, three significant figures. Here, 1, 2, 3, 4, four significant figures. Here, 1, 2, two significant figures. And so rewriting things in scientific notation is a good way to see how many significant figures do I have. You don't drop the ending zeros when you write it in scientific notation, but you do drop those beginning ones. And so that's a good way to remember which ones are significant. Now, when you talk about adding and subtracting significant figures, then there are rules that apply. And so when you add something that is less precise than something else, then it kind of skews the precision of your answer if you don't recognize these operations. The first rule is when you're adding and subtracting. Measured data must be the same kind of data with the same units. Okay, so first and foremost, you have to add numbers that have the same units. The sum or difference cannot have greater precision than the least precise measurement. So here, when you're adding and subtracting, you look at the least precise, and that's what you're going to use for adding and subtracting. All right. So hopefully you notice this first problem here is that we have meters and centimeters. We cannot add this until they have the same units. So I am going to convert to make sure that I have the same unit. So we're going to take this 64.5 centimeters and we are going to convert it. Now remember, my centimeters is on top. And so if I'm converting centimeters, my centimeters needs to be on bottom and my meters on top. And so 1 meter, the same as 100 centimeters. When you multiply across, divide by 100, you're going to get 0.645 meters, right? So now I'm going to have my 1.54 meters, and I'm going to add to it my 0.645 meters. Now, when I look at precision here I only have two decimal places. Here I have three. So my last significant figure here is 4. Most precise here is that 5 here. Well, when I add those up, I get 2.185 meters. But this was my most precise, and I only measured to the hundredth place for this one, right? So if I only measured to the hundredths place, the most I can measure when I'm adding, subtracting is the hundredths, which means I have to round this. So I look to the right, it is a 5. I'm going to say 2.19 meters. That's how I know where to round for this one. I take my least precise measurement, hundredths place here. So my answer has to be in the hundredths place. The next rule deals with multiplication and division. So this is products and quotients. Cannot have more significant figures than the measurement with the fewest. So we're no longer talking about precision, we're talking about significant figures. All right, so precision is how far out that decimal place went. The significant figures goes back to our rules of adding up our significant figures. The product or quotient of a measured data and a pure number should not have more or less precision than the original measurement. All right, so if you're multiplying and dividing significant figures, you're going to use the lowest number of significant figures. If you're using a pure number that was measured like counting, then you're not going to have any less precision in the original measurement. So this is find the area of a rectangular solar cell array that is 10.3 meters long and 3.7 meters wide. All right, so in this case, first of all, make sure they're the same units, and they are. And if we want area of a rectangle, that is just length times width. So we're going to take the 10.3 meters. We're going to multiply it by 3.7 meters, and we will get 38.11 square meters. Well, let's count our significant digits. This 10.3 had 1, 2, 3 significant digits. This one had 1, 2 significant digits. Remember, with multiplication, you use the least number of significant digits, meaning my answer can only have 2 significant digits. Right now it has 4. So I'm going to count. I can only use these 2 significant digits. I'm going to look to the right. It is a 1, so I leave it. 38 meters squared. Let's look at this third rule. Compound calculations. If the operations are all the same kind, complete the operation simultaneously using standard order of operations before you rounding. So if a solution requires both addition, subtraction, and multiplication, division, do not round intermediate solutions. All right. So round at the end. Do all of your calculations, determine your significant digits, and then round your final answer. Don't do it in between. That's what these are telling you here. So the question at the beginning was, why can't I report all 10 decimal places? Well, Calculators don't determine significant figures. When you put the numbers in, it's going to spit out as many digits as the calculator can give you. But scientific work is only valuable if it has integrity. And so rounding your answers to the precision of your instruments and to the precision of your given calculations is important because it tells the reader how precise you are. And if you gave all the digits, they would actually read it that your instrument was as precise as all those digits. And that would not be an answer that came across with integrity because it seems like it's more precise than it actually is. And that's why it's important to use significant figures.